All right. Well, last day of circuits for the week. Not much to say in the way of announcements other than that I didn't actually get the homeworks graded. Generating that solution set took forever because the solutions as provided by the textbook publisher are pretty much useless. And I think they solved every single one of the Thevenin problems using superposition in some way, which seems pretty pointless to me. But so that's what they had done. I wanted to change that so it was a little bit more useful. So those got finished yesterday, although I didn't manage to post them until this morning. But they are there, so you can take a look at it. And I'll do the grading when I get back to my office today. So quizzes, I didn't even bother looking at them. I think that we'll have to, on Monday we'll take a look at it because I should have them graded by then. But it should have been, I think, simpler than some people made it out to be in that on that left-hand loop with the dependent source. If you just wrote the KVL equation around it, you should have come up with something like negative 2Vx equals 12, I think, or equals 6, whatever the independent source was. And so then Vx equaled negative, I think it was negative 3. And then the open circuit voltage was just the voltage across that dependent source. So it was 9 volts, negative 9 volts. But and then specifically one of the things that I did do to make sure that the problem didn't get too weird is that I did stick in that resistor on the right-hand side so that when you're solving for the short circuit current, that the question didn't get too weird in terms of writing an equation with like no resistors on the right-hand side. Yeah, so as soon as I started working on that one, I was like, ooh, I need to put a resistor in here. So, but when you're solving for the open circuit voltage, there's no current running through that part of the circuit, and so there's no voltage across that resistor, and so all of the open circuit voltage would be the same as the voltage across the dependent source. So I designed it to try to be easy as a problem like that can be, I guess. But so homework was posted yesterday or something like that for this chapter for the transient analysis stuff that'll go on. What I'm kind of expecting at this point, and it depends on exactly how far we make it through the second order material today, but probably something like a Wednesday, maybe Thursday kind of due date for that homework. So, any questions or concerns or anything? You guys familiar with Agate Street around here? What's that?
I live on it.
You live on Agate? Well, when you start riding a bicycle up Agate Street, people look at you funny. But they're also very encouraging. Like, you're almost there, and I think he was lying, because I think I was about halfway up when he was telling me I'm almost there. So, all right. So, what we're going to look at today, flipping through my notes, the first thing is to do a Thevenin equivalent, or not a Thevenin equivalent, but do a first order transient circuit that includes a dependent source, because just as a bit of a reminder of how all that stuff is supposed to happen, if you were to look, you'd see that the better part of a page and a half is the work for that one. And I wish I could remember what this work was even for. Is it the continuation? Oh, it's the continuation of the work for this first problem. And then we'll start talking about second order circuits. And the way we're going to deal with second order circuits is somewhat more just cookbook and not doing anything particularly odd. But so let's get started with this first order dependent source circuit. Should be exciting beyond all get out. All right, so here's our circuit. All right, so there we go. You got a 36 volt source, 2 ohm resistor, 12 volt source, and this switch is at this position originally. In other words, the 36 volt source and the 2 ohm resistor are essentially not part of the circuit when we start. And when the switch transitions from this position to the other position, then the 12 volt source will go away. And then we have a 4 ohm resistor with some current IA that's running through it. It's worth noting the IA because that's the parameter on which this dependent source is dependent on. We have a 3 Henry inductor and a 6 ohm resistor, and it's the voltage across the 6 ohm resistor that we're interested in trying to deal with. So that is our circuit. For the most part, again, we're gonna, the same rule that we established like during the first or second week of class about dealing with circuits that contain dependent sources holds for these circuits too. Analyze the circuit as though it was independent and then sort it all out in the end. So again, then our first step is, all right, we'll assume that the form of the solution is the K1 plus K2 e to the negative t over tau. And the only place where the dependent source is going to become, a problem, as you might call it, is when we're actually solving for tau, because to find the Thevenin resistance, we're going to have to find the open circuit voltage and the short circuit current. So, this one, yeah, it's a current dependent voltage. No, it's a voltage source that's putting out 2 times IA volts. So
Isn't IA a current though?
it is, but this is a current dependent voltage source.
I don't see how you're getting voltage and so good, that's all.
I think in general we don't always like to see things like that. I think we kind of naturally want to see voltage-dependent voltage sources and current-dependent current sources, but it seems like even on some of the homeworks you've seen, you may have seen a current source that was of the value. I think this was even in the last homework problem.
But I can see voltages divided by K is in milliamps, but 2 times a milliamp is still going to be in millies.
I guess the thing to bear in mind is that all of the resistors in this particular are in the ones or tens of ohms, and so it works out more reasonably. Otherwise, yeah, it would need to be something like 2000 IA in order to make any kind of sense. So, second step then, the first step is to assume this form. The second step is to solve for the value of the storage element at time equals 0 minus. And in this case, because it's a an inductor will solve for the current that's running through that inductor. So the circuit at time equals 0 minus has the voltage source of the 12 volt source, this 36 volt source, the 2 ohm resistor, they're gone. We have the 4 ohm resistor with the current IA running through it. We have a short circuit here. We have a 6 ohm resistor here and the dependent voltage source here. So, and the thing that we want to solve for is I sub L. So that's not a terribly bad excuse me, a terribly bad circuit to solve for. Trying to figure out exactly what I did with my work here. Let's go ahead and I would just do this as a loop analysis or mesh analysis. Whatever we solve for as I2 is going to give us the current through the inductor. We've got, around the left-hand loop, we've got negative 12 plus 4 I1 minus I2 equals 0. And going around the second loop, we've got 4 I2 minus I1 plus 6 I2 minus 2 I sub A equals 0. So we wrote the KVLs assuming that, or acting like that source was independent. Now we need to write something that qualifies IA as something that we can use. IA, in terms of other circuit parameters, is just I1 minus I2. So, simplifying the first equation, we have 4I1 minus 4I2 equals 12. Simplifying the second equation, we get, so that's going to be negative 2I1 plus I2, or 2I2 when we get there. But so we've got 4I2 minus 4I1 plus 6I2 minus 2I1 plus 2I2 equals 0. So we can simplify that one more time to get all the terms together. We have a negative 4I1 and a negative 2I1, which gives us negative 6I1. We have 4, 10, 12 I2. So here are two equations that we would solve simultaneously. See what the good old calculator says. We have two equations, 4, negative 4, 12, negative 6, 12, 0, solve. So we get that I1 equals 6 amps, and I2, I2, which is the same as the current through the inductor, is 3 amps. So, that's the first thing that we need. So now we'll analyze the circuit with the switch in its new position. We'll replace the inductor with a 3 amp current source and start figuring out what's going on. So, see if we can keep both of these around. So there was the original circuit. Now the switch is opened up, or it's not just opened up, but it's changed position. So now the 36 volt source and the 2 ohm resistor are part of the circuit. The 12 volt source is not. Come down for the 4 ohm resistor. This is the 2 ohm resistor. This is the 4 ohm resistor. The current I sub A flows through there still. We need a current source of the value of 3 amps, which is standing in for our inductor. 6 ohm resistor, dependent source, 6 ohms. This is going to be V0 of 0 plus. So, how hard is this one to solve for? V0 of 0 plus equals the resistance times the current that's flowing through the resistance. So what's the current that's flowing through that resistor?
3 amps.
Yeah, it's 3 amps. It's just the 3 amps that are flowing from that current source. So pretty much nothing to do there. Almost nothing to do there. And so the original, that V0 of 0 plus is 18 volts. So we'll stick that away, something that we'll need a little later. Now we draw the circuit at time is greater than 5 tau. So this was at time equals 0 plus. This is time greater than 5 tau. 36 volt source still there. 2 ohm resistor, 4 ohm resistor. Now the inductor acts as a short circuit. So we've got the 6 ohm resistor and the dependent voltage source. So this is 2, 4, 6, 36. 2I sub A, and this is V0 of infinity. What seems, you could do this as a loop analysis or a mesh analysis. What is actually going to be, I think, somewhat easier is to do it as a nodal analysis. And to recall that, I mean, you can almost think, well, I can pull this 6 ohm resistor and just move it up onto the top part of this branch, and it doesn't change the circuit configuration at all. It just changes how we kind of visualize the circuit. And what you have then are two voltage sources, and it makes it so we really only have to write the single node equation. And so that single node equation will look like V1 minus 36 over 2 plus V1 over 4 plus V1 plus 2IA over 6 equals 0. And it becomes a plus because it's V1 minus a negative 2IA. So we just get rid of that. So that's our first equation. We do still need to write an equation that relates IA to one of our circuit parameters. And fortunately, it works out very nicely that the current IA is just equal to the node voltage V1 divided by 4. So we can take this information, shove it up into our first equation. To kind of make life a little easy, let's take and get rid of all of these fractions first. Looks like the common denominator is going to end up being 12. So multiply everything by 12. So you get 6V1 minus 36 times 12 is a very large number. But it's only times 6. So that's a slightly smaller number, which is 216 plus 3V1 plus 2V1 plus 4IA equals 0. So put this information in, and isn't it convenient that we have 4IA times V1 over 4? So let's combine the terms that we know already. So we've got 6V1, we've got 9V1, we've got 11V1. Plus 4 times V1 over 4 equals 216. So those kind of cancel out. You end up with 12V1 equals 216. 216 divided by 12 is 18 volts. So That's only part of the problem, though. We need to now find what that voltage is, V0, across the 6 ohm resistor. So that is going to be V1 minus well, the voltage over here, which is 2IA. So V1 we solved for is 18 volts. 2IA we solved for, well, we didn't solve for yet, but IA is V1 over 4, so that's going to be 2 times 18 over 4. Yes, it's minus the negative, so it's plus. Thanks. So 36 divided by 4 is 9, so it's 18 plus 9, or 27 volts. So that's the second thing that we need. Now the next step is to calculate the Thevenin resistance from the terminals of the storage element. And this is where, if this process hasn't already been long enough, it gets another step longer, because the only way to solve for that is to do the solve for the open circuit voltage and the short circuit current, and the ratio of those two will give you your Thevenin resistance. So we have to kind of draw the circuit 2 more times, I guess, but we've got a lot of the information cruising through, so we're making good progress at least. So the circuit at time greater than 5 tau then, again, we have the 36 volt source, we have the 2 ohm resistor, we have the 4 ohm resistor, 2, 4. This is where the storage element is. So we find the open circuit voltage across there. We've got 6 ohm resistor over here, and we've got the voltage source minus plus 2IA. This is 6 ohm resistor. Okay, so again, doing this is kind of tricky. This one is maybe not as fun as it could be, but will definitely challenge you. The key thing to remember here, as we step through this one, is that there's no current running through the 6 ohm resistor. However, that doesn't mean that there isn't still voltage around certain parts of this loop. So let's write this equation out just so we're feeling kind of comfortable with it. We've got the open circuit voltage will equal the voltage across the 6 ohm resistor minus 2 times IA, which is the voltage across that source, and then plus the voltage across the 4 ohm resistor. And actually I've got those, I've got these signs kind of screwed up. So this one, it doesn't matter so much, but that should be a plus, because we had plus VOC plus the 6 ohm resistor minus 2IA minus 4, the voltage across the 4 ohm resistor. So that should be a 4. But again, because there's no current running through this branch, the voltage across the 6 ohm resistor is 0. We need to solve for 2IA, and the voltage across the 4 ohm resistor is the 4 ohms times the current IA. So that's kind of handy. It means that it's going to be important to solve for IA, but fortunately that's pretty trivial, because again, because there's no connection, this voltage source can't contribute to anything, and you basically have a single loop circuit. Single loop circuit with these two resistors in series gives us 6 ohms. Divide the 36 volts by 6 ohms and you find that IA, it's 36 divided by 4 plus 2 equals 6. So we stick that up in here, and basically this one had boiled down to 6 times IA, so that's going to be 36. That's the open circuit voltage. The short circuit current, this one is one where if you're kind of paying attention, you'll notice something about this particular circuit. Which is that it looks an awful lot like our circuit for time greater than 5 tau. Let's see, you can see both of those. This is the circuit for time greater than 5 tau, just with the inductor being there, I suppose. And here's the circuit so that we can solve for the short circuit current. And I don't know about you, but I don't really see any differences between those two circuits, which is nice. What it means is that you can reuse all of the work that you did in the previous step. And unfortunately, I think that, I'm trying to think through this to make sure that what I'm saying is right, but I think that will only nicely work when you're working with an inductor. If you're working with a capacitor, you won't be directly solving for anything like that, but the circuit will essentially look the same when you're solving for the open circuit voltage and the circuit at time greater than 5 tau. But so what we need is the short circuit current. If we know what the voltage is across the 6 ohm resistor and we divide it by the 6 ohms, that should give us the same information that we wanted. We already, let's see, make sure that's right. Yeah. So we know from this analysis that there were 27 volts across that, and there's 6 ohms of resistance. So our short circuit currents will be the 27 volts divided by 6 ohms, which is the same as long as I did the math right, divided by 3, yeah. So that's 9/2 or 4.5, I guess. So the key there was recognizing that this version of the circuit and this version of the circuit were exactly the same. You can go through all of the analysis again if you want to, but why bother? I mean, honestly, I think it wasn't until I taught this material, not this past spring semester, but the year before, that I realized that when I was solving for the short circuit current here, that I was doing all of the exact same analysis that I had just done up here. So you can save yourself a little bit of work. So now we have our open circuit voltage and we have our short circuit current. So the ratio of those two will give us our Thevenin. We put the open circuit voltage of 36 on top, the 4.5 amps of the short circuit currents on the bottom, which should give us, gives us 8. So all of that. And so our Thevenin equivalent for that original circuit, oh, no, that's not what we're doing. We're doing the stuff. So we've got V of 0 plus was, it's on here somewhere, I'm sure, is 18 volts. V of infinity is 27 volts. Our Thevenin is 8 ohms. So tau is L over our Thevenin. And the original version of that was was 3 henries over 8 ohms. K1 just equals the V of infinity, which is 27. K2 equals V of 0 plus minus V of infinity. So that is 18 minus 27, or negative 9. So the final form of our equation, the voltage across that 6 ohm resistor as a function of time from time equals 0 is we have 27 minus 9 e to the negative t over 3/8, or in a slightly prettier version, 27 minus 9 e to the negative 8t over 3. Any questions or concerns about that? The process is the same as what we've been doing in the past. We solve for the initial condition across the storage element, replace the storage element with an independent source, do all of our analysis to find the value of the parameter at time equals 0 plus, at time greater than 5 tau, and then the only wrinkle in the process with these dependent sources is that to solve for the Thevenin resistance, we have to find the open circuit voltage and the short circuit current. A little long, a little unfortunate that we have to do it that way, but such is life. So, do you want to see any more of these, or are you feeling pretty comfortable with? So in general, any of these first order transient analysis circuits? Okay. Well, if you do have any questions, please let me know. So, second topic in this chapter are second order RLC circuits, which are, this is where the process, I think, honestly breaks down a little bit, and so it ends up being of more value to kind of keep this material at 10,000 feet and not worry about the details a ton, because the better way to solve these is using Laplace transforms and stuff. But we have a fairly straightforward kind of cookbook way of approaching these problems. So what we're going to be doing is we're going to take a circuit, we're going to put one, for our purposes, we're going to put usually, if it's not exactly one resistor, one inductor, and one capacitor, it'll be something that we can reduce to one resistor, one inductor, and one capacitor. And it will either be with each one of those elements in series with each other, or all of the 3 elements are going to be parallel with each other. Because we have 2 storage elements in there, the behavior of the circuit is characterized by a second order differential equation. And the form of the solution will take one of 3 normal differential equation solution forms. And fortunately, they're pretty easy to actually analyze these things. It's not as difficult as you might think. So all of these equations revolve around this parallel RLC circuit. We've got some resistor, we've got some inductor, and we've got some capacitor. We've got values C and L and R. This is some current that comes out of the source. And this is our single node in the circuit, because I guess this is, as in some of our earliest circuits, this is a single node pair circuit. And if you look at what is the current that's running through all of these elements, the current in the resistor is that voltage V over R. the current in the inductor is 1 over L times an integral of from some time t0 up to t of the voltage across there, and then the initial conditions of the at time equals t0, and then you've got the capacitor times the derivative of the voltage with respect to time, and that all equals what's coming out of the source. And that's just the KCL equation at this node, right? That's this is the resistor. This is the craziness for the inductor, and this is the somewhat less craziness of the capacitor. And to get, so we take the derivative to get rid of all of the, to get rid of the integral for the inductor. So we're taking dV dx or dV dt, and what that ends up with is, and if you rearrange the terms, what you get is c times d squared v over dt squared plus 1 over r dV dt plus v over L equals di spes of dt. So that hopefully looks like a fairly straightforward second order differential equation. Nothing particularly weird there, I don't think, but it has been 10 years since I took differential equations, so my grad class this spring was a little bit rough sailing when he started throwing differential equations up onto the board. I was like, oh, I have to remember that stuff now? So, so that's the differential equation that characterizes this parallel RLC circuit. But rather than necessarily dealing with it like that, we're going to think about it as just being, it's a differential equation, it's a second order equation with constant coefficients, which can be analyzed in the normal fashion of dealing with that kind of differential equation. And so we'll think about it more in terms of, and for the most part, this is going to be the last time that you're going to see the differential equation form of the circuit from me. We're going to look more at the characteristic equation. We get rid of this c that had been in the coefficient on the second order differential, and we end up with s squared plus 1 over RCS plus 1 over LC equals 0. And solving for the roots of that characteristic equation are going to drive our analysis of the circuit. And yeah, so good old quadratic formula to solve for these, right? So you can characterize these coefficients on those S terms in a couple of different ways. If you look in your textbook, and when I was originally preparing this material a few years ago, I looked at this and I'm like, this doesn't look familiar at all. He characterizes the coefficient on the first order S term as 2 zeta omega naught, and the final term is omega naught squared. I had my circuits teacher that went through this stuff always just called the zeta squiggle. But she used it in a different context, and I don't even remember what it was. But when you dig into the textbook, what it says is that zeta, or squiggle, is the damping ratio, and omega naught is what we call the undamped natural frequency, or the resonant radian frequency. It's the same name, and it'll show up a lot, again, in a couple of chapters. I don't find, when I thought about how did I learn this material, how does Dr. Mbardar teach this material, what is kind of the consistent face, I don't think anybody in this department uses that. What we use is a slightly different version, which comes from the Nilsson and Rydell textbook, where they characterize those coefficients as, instead of squiggle times omega naught, we have 2 alpha times S and then omega naught squared. And so they're the same they're the same. The last term is the same. They give it a slightly different name as the resonant radian frequency instead of the undamped natural frequency. It's the same thing. But instead of dealing with the squiggle, we're going to deal with 2 times alpha. And for parallel circuits, it's important that, I think this is right, that for parallel circuits, this one and this one are, it's only good for parallel. If you can read that as saying parallel. I think it's alpha will change when we start looking at series circuits, but omega naught will stay fixed at 1 over the square root of LC. Solving, part of the reason that we like, or at least I like, alpha instead of 2 zeta is because there's not an easy way to solve for this one. That's really nasty to solve for. Whereas here, alpha is pretty straightforward to solve for. It's 1 over 2 RC. So that is why we use that one instead. So kind of what is the meaning of all of that stuff? Why do we care about all of these things? In my horrible pun at the top, it's all Greek to me, blah, blah. So why do we care? If we solve for those terms of alpha and omega naught, that gives us an easy way to solve for the roots of the characteristic equation. And this just simplifies out all of the quadratic equation stuff. So you have negative alpha plus or minus the square root of alpha squared minus omega naught squared. And so again, this is decomposing something that is really probably fairly difficult and making it something that's much more straightforward and kind of plug and chug. So you look at the circuit that you've been given, you go back and you say, well, if it's a parallel circuit, then I can solve for alpha as 1 over 2 RC. I can solve for omega naught as 1 over the square root of LC. And then I plug it into these 2 equations to solve for the characteristic roots. So, but just like the first time you encountered the quadratic formula, you could wind up with one of 3 solutions, right? You could end up where the 2 roots are exactly the same. You could end up where the roots are real and unequal, or you can wind up where they are complex conjugates. And again, so we're already starting to get into, start thinking about the square root of -1 as being j again. So when you have a circuit that has real and unequal roots, it's called overdamped. And that has a specific behavior in terms of the way that it reacts and the voltage that you're looking at. And normally when we're looking at parallel RLC circuits, we're looking at the voltage across the elements. But the voltage reacts in a specific way, and I think the figure is on the next slide. Underdamped behaves in a slightly different way when you have those complex conjugates, and if they are the same, then it's called critically damped, and it exhibits a behavior we call ringing as it settles down to its final form. And so what makes alpha and omega naught kind of powerful is that it makes it very easy for us really at a glance to determine which of these is going to happen, because you can look at the second half of each one of those root terms and say, well, if alpha squared is less than omega naught squared, well, then you're going to have the complex conjugates, right? Because you're going to have a negative number and that's under that square root. If alpha squared is greater than omega naught squared, then you're going to have the case number 1 with the real and unequal roots. If it works out by some miracle that alpha and omega naught are the same, then you're going to have a critically damped system. Zeta can tell us this if we solve for it the proper ways, but there's no easy and kind of fun or simple ways to do that solution that I've been able to find, at least. So I prefer to use alpha and omega naughts anyways. So if a circuit is critically damped, you can, or it's underdamped that exhibits ringing, sorry. So an overdamped circuit has the behavior as shown on in the figure. A critically damped circuit rises a little bit quicker and falls a little bit quicker as well. And it's the underdamped circuit that exhibits the ringing, where it kind of bounces up and down. And I think that largely has to do with the it has to do with the storage element, but I don't remember exactly what the cause is specifically. But it's the ringing of the magnitude of the ring or the amplitude of the wave is constrained by either e to the negative alpha t or negative e to the alpha t as those decompose down. So does the ringing. So eventually they do settle down, but that's the form that the equation or the response takes if you were to try to graph it. So how to determine the damping? We already kind of talked about this already. But if omega naught squared is less than alpha squared, given the forms of the equation, then you'll have the real and unequal roots, and the circuit is overdamped. In that case, if you were to solve for it, zeta would be greater than 1. If omega naught squared is greater than alpha squared, then it's going to be underdamped. You're going to see the real or the complex conjugate roots. And then if omega naught squared equals alpha squared, they're the same, then obviously then the circuit is it's going to have the same root, one of the same value of the same root. And it'll be a critically damped circuit. Now, the reason that it's worth solving for those things and looking at them ahead of time is that without bothering to actually solve the differential equation, the form of the damping can tell us what the form of the differential equation looks like. But before we get into that, we'll take a quick look at calculating damping kinds of things. So here's a parallel RLC circuit. You don't even need to see the thing in order to work on this problem because it's all basically formulas and plugging stuff in. So a parallel RLC circuit has a resistor that is 200 ohms, an inductor that has 50 millihenries, and a capacitor that is 0.2 microfarads. And what we want to do is we want to find S1, we want to find S2, and what is the response? What is the type of damping exhibited by this circuit? Is it overdamped, underdamped, or critically damped? And because it's a parallel circuit, alpha equals 1 over 2RC. Omega naught equals 1 over the square root of LC. So plug and chug of 1 over 2 times 200 times 0.2 micros. 2 times 200, and let's try multiplying instead of adding, times 0.2 e negative 6. Flip that, and we get a value for alpha that is 12,500. So this will be 1 over 50 millihenries times 0.2 microfarads. 50 e negative 3 times 0.2 e negative 6. Sounds like there's a tornado starting up in here. And then flip that, oops, take the square root of that. Where's my square root button? And then flip it, and you get that omega naught equals 10,000. It's often useful at this point to just go ahead and calculate what alpha squared and omega naught squared are so that you can compare them more directly when you start thinking about the roots. So let's see, alpha squared 12,500 squared is a very large number. Let's see, I'll just write the digits 156250000. And omega naught squared as 10,000 is a 1 followed by 1, 2, 3, 4, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So, comparing alpha squared and omega naught squared, we see that omega naught squared is considerably larger than, alpha squared is considerably larger than omega naught squared. And that means that the form of the response is overdamped. And you might have to look back at the previous slides to remember that, but it's an overdamped circuit. And so we can just plug in and solve for S1 and S2. S1 equals negative alpha plus the square root of alpha squared minus omega naught squared. So we subtract, so what is that exactly? 156,250,000. Yeah, that's right. Minus 100 million, I guess. 1, 2, 3, 4, 5, 6, 7, 8. Take the square root of that. And that gets us, so that's negative alpha, which is negative 12,500 plus 7,500. Whoops, just 7,500. So that equals negative 5,000. There's our first root. And then we have S2 equals negative alpha minus this quantity of 7,500. So that's negative 12,500 minus 7,500, which should give us a negative 20,000. Not much more to say about that one, I suppose. And so that's what, it gives you an idea of what you need to kind of get comfortable with doing for the rest of this chapter. So we found that it's not too terribly difficult to determine the form of the damping in the circuit. You just kind of plug things in, compare alpha squared to omega naught squared, and see what's going on. So what we're going to be doing for all of our solutions when we actually see circuits of this form is pretty cookbook. We're going to, for overdamped circuits, the circuit is going to take this response. And in case it's not entirely clear, that says that the voltage across all of these elements equals some constant K1 e to the S1t. So it's important to solve for the roots of the characteristic equation because they do factor into the final version of the solution, plus K2 e to the S2t. Now it worked out in our previous example that both S1 and S2 were negative, and so you get the kind of the damping response that you looked for. K1 and K2 must be determined from initial conditions, and I think that's fairly straightforward with solving differential equations. You need some sort of initial condition. The cookbook way of finding K1 and K2 is that whatever the initial voltage was across all of those elements, they're all in parallel, so they all have the same voltage across them, is just the sum of K1 plus K2. And then the easiest way to solve, then you need, from a differential equation solution point of view, you need a constant that gives you from the first derivative, right? So what we can kind of almost cheat and do is say that, well, the derivative of the voltage at time 0 is the value of the current through the capacitor at time 0 divided by the capacitance equals S1 K1 plus S2 K2. So again, you just kind of plug and chug, just run with it. V0 is either given to you or it's determined by some very simple circuit analysis. And again, you have to remember when you're doing that initial circuit analysis, if it's there, is that the inductor is acting as a short circuit, the resistor is there, the capacitor is acting as an open circuit. And so so normally what you would see is you'd say, all right, so I will give you the initial voltage across these things, and you will have to use a little bit of know-how on how to solve for what the rest of the parameters are, at least in terms of what is the current through the capacitor. Or it might give you something like the current through the inductor is X number of amps. And so you need to start thinking, okay, well, if there's that much current running here and there's this voltage or whatever, you can solve for the other things. So that's it for parallel overdamped responses. I'll give you at least one quick example of doing a parallel overdamped response. We have a parallel circuit. Just for kicks, we'll draw the circuit, but it's not like it's much different from the first version of the circuit that we saw. So we have a resistor of value 2 ohms. We have an inductor of the value of 5 henries. We have a capacitor that is 1/5 of a farad. We know that the initial conditions across the capacitor is the voltage at time 0 equals 4 volts, and that the current through the inductor at time 0 was -1 amp. And we want to find the voltage, which is the same voltage across all of the elements for t greater than 0. So to some extent you can kind of cheat and say, well, I told you this is a parallel overdamped example, so we can assume that it's going to be of the form that we just talked about. But we can kind of solve for that too and see that it is the case. And in general, the way that you're going to start all of these second order problems is to just go ahead and start solving for omega naught and alpha in order to figure out what the form of the solution is and whatnot. They're the same as before. Alpha is 1/2 RC. Omega naught equals 1 over the square root of LC. So this is 1/2 times 2 times, I guess, 0.2. So 2 times 0.2. Flip that. And we get that alpha equals 1.25. This is 1 over the square root of, how convenient, 5 times 1/5. And so that will be 5 times 1/5 is 1, square root of 1 is 1, 1/1 is 1. And so omega naught equals 1. So again, we can plug in real quick and say 1.25 squared is 1.5625. Conveniently, omega naught squared. I can do that one in my head. 1 squared is still 1. And alpha squared is greater than omega naught squared, so we've shown that it is indeed an overdamped circuit. I mean, there's not much to it there. So we know that it will take the form of K, that the voltage will equal K1 e to the S1t plus K2 e to the S2t. Our initial conditions that we have to solve for K1 and K2, we know that the original voltage across all of the elements, but because they're in parallel, the fact that it's across the capacitor is pretty straightforward. But either way, the voltage at time 0 is equal to 4. So K1 plus K2 equals 4. Now the next one is where you have to be, I suppose, a little bit creative. One of the things that I forgot to draw is we defined the current through the inductor as going down that way, and the initial conditions tell us that it's actually flowing up. And we defined it as flowing down, but it's negative, so it's flowing the other direction. So we think about this a little bit and we say, okay, there's 1 amp of current that's flowing up into that node. And if there's 4 volts across the capacitor, there's 4 volts across the inductor, and there's also 4 volts across the resistor. Well, if there's 4 volts across the resistor and there's 2 ohms of resistance, then there better be 2 amps flowing through that resistor, right? It's pretty straightforward. So if there's 2 amps flowing that way, there's 1 amp flowing that way, then, well, what's the current flowing through the capacitor? Yeah, it's 1 amp and it's going this direction. So probably, and my notes are not helping me here, yeah, we just define it as 1 amp, right? Yeah. So that's the thing that we need, is that it's a 1 amp current that's flowing through the capacitor. And yeah, so next thing that we need to do, and we probably should have done it before, was to solve for the roots S1 and S2. This one is negative alpha plus the square root of alpha squared minus omega naught squared. Alpha squared minus omega naught squared. So that's negative 1.25 plus, let's see, omega naught squared is 1.5625 minus 1 second square roots, whoops, second. So the square root there is 0.75. So that should give us a negative half. And S2 is negative alpha minus the square root term of alpha squared minus omega naught squared. So that'll be negative 1.25 minus 0.75, or negative 2. So equations that we need to solve for our final parameters, this is one of them, K1 plus K2 equals 4. The other one is that the current through the capacitor divided by the capacitance, or 1 over 5, 1 over a fifth, equals S1 K1, so we've got negative 1/2 K1 plus S2 K2, which is negative 2 times K2. So now we have 2 simultaneous equations, 2 variables. We solve for K1 and K2. Plug them in, make sure we get the right answers here. So 1 K1 plus 1 K2 equals 4, and negative 0.5 K1 minus 2 K2 equals 5. And must not have put that in right. 1 plus 1 is 4. Negative half, negative 2. 1 divided by 1 divided by 5. I'm not getting the same answers. Why am I not getting that right? It's supposed to be... There we go. This didn't feel right to my analysis when I was talking about it. But this current through the capacitor, it is of the magnitude of 1 amp, right? It has to be. But it is -1 from our point of view, that, you know, I sub C is -1 amp. And it's one of the things that is hard for me to wrap my mind around sometimes too. It is of magnitude 1 amp, but defining all of these things as I sub R, I sub L, I sub C, with the voltage across the capacitor like that. So it has to be -1 amp, which means that this is -1 divided by 1/5. And that will get you proper answers. So that's K1 equals 2, and K2 equals 2. And we plug those into the form. We've solved for everything else. So we get V equals K1 to e to the, I guess, say -t/2, plus 2 e to the -2t. And I hate when I do that. It's important to keep the current direction straight so that you get the right sign, or otherwise you'll get some very kind of ugly numbers. Yeah.
The 4 volts.
This
yeah.
one?
Is that
It was-
given in the problem?
Yeah, it's given in the problem. You may occasionally see problems where there will be, so this is, let's draw it in a different color just so it comes across. You may see occasionally problems where there will be like a voltage source with a switch that opens at time equals 0, or something like that, which gives you the initial condition in kind of a cheap way, I suppose. But and I forget which problems I assigned in the homework, but that kind of thing might show up. One other problem that's probably worth noting at least a little bit is that I think the very last of the first order transient analysis has like 3 capacitors in it. And so you have to combine the capacitors to get it down to a single storage element. But it shouldn't be too scary. It looked like a pretty straightforward problem. So that's a parallel overdamped response. And really it's just a bunch of using formulas, putting in the values, not a lot in the way of actual circuit analysis. But you can screw things up pretty quickly if you do screw up the circuit analysis. And I want to fix my notes so I don't do this wrong in the future. Yeah. Okay. So that's overdamped response. I think we can cover the underdamped response at least real quickly. The underdamped response has a similar kind of thing, a similar kind of form, except this case, underdamped means that you had the real the complex conjugates. So the roots are given as negative alpha plus or minus the square root of negative omega naught squared minus alpha squared. And when you solve that all, it's alpha plus or minus the square, or j times the square root of omega naught squared minus alpha squared. All that being said, we don't really use the roots for anything in this particular application. For convenience and for understanding, we're going to introduce a new a new frequency, which is the damped frequency. We're going to call it omega sub d, or just omega d, and that's given as it would be what the coefficient is on the complex term or on the imaginary term in your root. So then the roots would be rewritten as being S1 equals alpha plus j times omega d, or negative alpha minus j times omega d. All that being said, when you look at the final form of the response, you have a constant B1, and it's important. One of the reasons that on the overdamped response we talked about a constant K1, and here we talk about a constant B1. They are different constants. You solve for them in slightly different ways, or they come from the initial conditions in slightly different ways, and so we want to differentiate between those. So you have some constant B1 times e to the negative alpha t times the cosine of omega naught, or omega d times t. The second term is B2 e to the negative alpha t times the sine of omega d times t. So, in other words, boy, the roots of the characteristic equation didn't show up anywhere in the final form of our solution. So all we're going to do is, if we determine that it is going to be an underdamped solution, then we'll solve for omega d instead. Then we'll solve for our coefficients B1 and B2. Where B1 is really easy. Whatever the initial voltage is, that's B1. That's as hard as it gets. Then again, we're going to calculate what the current was that was running through the capacitor divided by the capacitance itself, and that'll give us negative alpha times B1 plus omega d times B2. You got the two equations, two unknowns, and you solve for those simultaneously. Let's see if we can get through at least part of this. We've got like 3 minutes, so see what we can do. Same parallel circuit. In this case, we have R equals 20 kiloohms. We have L equals 8 henries. We have C equals 0.125 microfarads. We have an initial condition across the capacitor as 0 volts. And we have an initial current through the inductor of being negative 12.25 milliamps. So that's our setup, and what we want to still find is the voltage with respect to time for time greater than 0. So solve for alpha, which is 1 over 2 RC. Solve for omega naught, which is 1 over the square root of LC. So this is 1 over 2 times 20K times 0.125 micros. And I'm going to hope that my math is right, and that alpha here equals 200. 1 over the square root of L, which is 8, times 0.125 micro, and that should give us 1,000. We plug it in. So in this case, it's very clear that omega naught is not just larger than alpha, it's a lot bigger than alpha. And so this should be an underdamped circuit. So we're not going to worry a ton. In my notes, I have solved for what the roots actually look like, but it's not really important because, again, the roots don't get used in the final form of the solution. What we will solve for is that term omega d, which is the square roots of omega naught squared minus alpha squared. So that is square roots of, I guess it's 1,000 squared minus 200 squared. And that gives us approximately 979.80. So the form of our equation is that B1 e to the negative alpha t cosine omega d of t plus B2 e to the negative alpha t sine of omega d times t. B1 simply equals the initial voltage across the elements, 0. B2, or the next one, so here we have to think about this one again a little bit and remember what our circuit looks like with the resistor, the inductor, and the capacitor. So it tells us in the setup for the equation that this current IL is negative 12.25 milliamps. Here's where we put a little bit of circuit analysis to work. If there's 0 volts across the capacitor, there's 0 volts across the resistor, and so there is 0 current running through the resistor, right? V divided by R. That means that there's no place for this 12.2 milliamps of current to go except down this way. And this time it is positive because there's no, if it's coming up this way and nothing's going that way, then it all has to go that way. And it's going the same direction that we've defined the voltage across the capacitor. So what that means is that we take the 12.25, and I hate my notes, say 12.25 milliamps divided by the capacitance, which was 0.125 microfarads, equals negative alpha. We solved for alpha, so it's negative 200 times B1 plus omega D, which is 979.80 times B2. Hey, and what do you know? B1 is 0, so that term drops off. 12.25 e to the negative 3 divided by 0.125 to the negative 6th. This is 98,000 equals 979.80 times B2. And perhaps if we hadn't rounded or something, this would work out a little nicer, but B2 equals about 100. And if you take it out far enough, it's 100.02 or thereabouts. So we have B1, we have B2, we have omega D. And plugging it into the final form of our equation, and I'm still going over, we get B1 e to the negative alpha t cosine omega d of t plus B2 e to the negative alpha t sine of omega d t. B1 was 0, so this whole cosine term drops out. B2 was 100.02 e to the negative 200t times the sine of 979.80 t equals the voltage. Okay, we got to be done. If you have any questions, let me know. Have a good weekend. Bye.